Archives, such as zip files, store multiple files together as one. In this unit, we'll see how we can list, create, and extract data that are held in archives. We'll go over various types of archives. These include the traditional tape archives used on Unix systems, archives used to hold together object files as libraries, archives used to package Java bytecode classes, and the zip format often used on Windows PCs. Finally, we'll also see how we can compress individual files. Let's first fetch an archive from the internet and list its contents. Notice here that the contents of the archive are never saved on disk as a whole.
To fetch an archive file from the internet, as you may guess, we use the curl command again. Here, I access the definitive Linux kernel archives by Linus Torvalds. My goal is to get an image of the Linux kernel, which is a compressed so-called tape archive file. After obtaining the data with curl, I pipe the output to the tar command, which stands for tape archive, and specify a few arguments. First, I use T to list the archive's contents. Then, I add Z, indicating that the archive file is compressed with gzip. With V, which stands for verbose, I list not only the names of the entries, but also additional information about them. For example, we get the size and the date of the last modification of each entry. Lastly, I use F to retrieve the file from a particular location rather than from a tape archive attached to the host. In my case, this location is the output of curl, which corresponds to the standard input of tar. By convention, many arguments that expect file names use a minus to convey the standard input or output. At the end, I pipe the result to head -10 to see the first 10 entries. That's how we list the entries of an archive file located on the web without its contents ever touching our disk.
Now let's extract the archive's contents. Again, the archive as a whole is never stored on disk.
Extraction works in a similar way with listing. We run curl and pipe the output to tar, but now we replace the T argument with X. As you may remember in the listing example, we used T to list the archive's contents. With X, we actually extract the contents of the file. Again, we choose the archive file to be the standard input with minus. Once the fetch and tape archive commands finish, I list the contents of the current directory. We see here a directory named Linux 5.6 RC2. To see its size, we can use the du command, which stands for disk usage. The file measures about 1 GB. Let's finally also list its contents to see the files it contains.
As you might expect, we can use tar to pack together many files into a single archive.
To create a tape archive, we use the tar command with the -c option. This time, I specify a regular file as an argument to F rather than the standard input. My goal is to create a tape archive named share.tar from the contents of the directory user share. Notice how tar warns us that it removes the daily leading slash from member names. This occurs to prevent any overwriting of the root directory during a future extraction of the archive. We can also create the archive on the standard output and then compress it. As above, I run tar -cf followed by a minus implying the standard output. Then I pipe the result to gzip, specifying a -c option, which means to compress the standard input. I finally send the compressed output to a file named share.tar.gz. Next, I compare the size of the compressed file with the size of the original directory. For the compressed file, I run the command ls-lh in order to see its size in a human-readable format. We get a total of about 300 megabytes. For the original directory, I run the command du-sh and we get a size of about 900 megabytes. Apparently, the contents of the directory were compressed to about a third of their original size. Because we typically compress the contents of the tape archive, tar allows us to directly create and compress archives. The way to do that is with the -Z option. In this way, tar creates an archive with C and in parallel compresses it with Z.
Interestingly, we can pipe the output of one archive command into another. This opens up tons of possibilities.
Consider as an example the directory user share dict. I want to copy the files of dict to another directory, for example dict2. First, I create this directory with makedir. Now, using an open bracket, I create a subshell. In this subshell, I go into the original dict directory that I plan to copy. Then, under dict, I run tar with the C option to create an archive of the contents of the directory. I specify a dot to denote the current directory. Similar to the previous examples, I send the output to the standard output using a minus. I close the subshell and pipe its output to a second subshell. In the second subshell, I change to the directory dict2 that I created above. Under dict2, I run tar again, but with the X option now. I do that to extract from the standard input the contents of the archive I previously created. Again, I close the second subshell, and this invokes both tar commands concurrently. The output of the first tar is piped as input to the second. In this way, we copy the contents of a directory dict to another, dict2. Note that this works because on Unix, each shell has an individual current directory for its processes. Listing the contents of dict2, we verify that it contains a copy of the contents of the original dict. Because it is common to use multiple directories with tape archive, tar offers the option C. With this option, we can directly specify the current directory that tar will change to when it runs. Consequently, to simplify the above example, I type tar -C. Then, I specify the directory where tar will change to before the creation of the archive. Similarly, I specify the directory where tar will change to before extracting it.
Object files, the result of compiling source into native code, are stored together in another format as libraries.
To access the contents of a library file, we use the R command. The options of R are similar to tar's. For instance, I use R with the options TV. T is meant to list the contents of the archive, while V displays them in verbose format. The archive I specify to use is the C library. Then I pipe the output to head to display the first few entries. In this way, we see the various object files of the C library. For example, there is an object file for starting a program, one for finding its version, some for errors, and so on.
Java class files are stored together in yet another archive format, the jar archive format.
With the Java Development Kit installed, we can use the jar command to access the contents of Java archives. Again, jar offers similar options with tar and R. Here, I specify the location of the JUnit archive. If you are not familiar with it, JUnit is a simple framework to write repeatable tests in Java. As an input, we get various directories where the JUnit's classes are stored.
Windows PCs use a very similar format, the zip file format.
To create a zip archive, we use the zip command. To access the contents of a zip archive, we use unzip. As an example, I run unzip to see in verbose format the contents of calculator.zip. As you can see, there is a lot of decoration here. There is the name of the archive and headers for the contents. But in general, the command works in the same way as tar and R.
In some cases, you might want to compress a single file. The tools you can use for this purpose are the bzip2 and gzip commands.
Let's go back to the compressed archive we created with the contents of the user share dict directory. Listing the contents of share.tar.gz, we see that it measures about 500 megabytes. Can we decrease its size? Let's give it a try. I run gzip with the arguments -dc. D stands for decompress, C means to use the standard input as the input of gzip, and the standard output as the output of the compressed results. Next, I pipe the output of gzip to bzip2, which is another compression program. Again, I specify the C option to use a standard input and output. Then, I redirect the output of bzip2 to another file named share.tar.bz2. Now, listing the contents of bz2, we see that it is actually smaller than the gz file. It turns out that bzip2 performs better than gzip, although gzip is a quite efficient compression program.
This concludes our unit on fetching data from archives. Stay with us.